what I titled this, a comparison. Okay, so that's what I said. I'll come back to this. So first, here's the definition of a periodic point. Let's say we have a function f hat of x, multi-valued function. You call that y, and let little f of x comma y be the minimal polynomial of that f hat of x. Then a periodic point is a algebraic number a for which there exists a1, a2 up to an minus 1, possibly in the completion, such that f of a comma a1 is 0, f of a1 comma a2 is 0, and so on. So you have these chain of equations. In other words, you start from a and you go to a1, a2, and come back to a. You may have seen, maybe the usual definition of periodic point is given in terms of iteration of functions, but this is exactly the same as that, because when I say f of a comma a1 equals 0, I'm saying a1 is f hat of a, and then a2 is f hat of a1, and so on. Okay. So here, at each step, for example, when I say a2 is f hat of a1, it could come from maybe a different branch of f hat. It's still not a problem for this definition. So, so in the header, I'm putting which case I'm talking about. So this is the case p equal to 2. So here, this is the continued fraction we look at. It's often referred to as the Ramanujan-Golnitz-Gordon continued fraction. It appears in his second notebook from the 2 volumes. It is also given by this infinite product expansion. And notice that it's very similar to the famous Rogers-Ramanujan continued fraction. So I would call this the case p equal to 5. The factor q power 1 over 5 here and the factor q power 1 over 2 there gives us another reason why I'm calling that case 2 and this one case 5. So this Rogers-Ramanujan continued fraction has been extensively studied in many ways. And for case 3, I'm using this cubic continued fraction, which is also given by this infinite product expansion. In fact, it's a modular function also. So, so this is the outline of what we will do. So previously, for the Rogers-Ramanujan continued fraction for p is equal to 5, it was shown that certain values of it that lie in the imaginary quadratic field with that discriminant condition, negative d plus or minus 1 mod 5, happen to be periodic points of a fixed algebraic function and also generate certain class fields. So the notation I'm using is sigma f for the ray class field of conductor f and omega f for the ring class field of conductor integer f. So we will show similar results for the case p equal to 2 for v of tau and the case p equal to 3 for c of tau. So this is what we do in the case p is equal to 2. So we show that for such a w, which is an algebraic integer, and there is a norm condition to make sure 2 splits into a product of 2 prime ideals. This is what we'll show. V of w over 8 for such a w is given by that expression in terms of pi, where pi is a generator of the ring class field of conductor f of p2. So this is what I actually have in the abstract. This is what I will show eventually. And then in the case 3, p equal to 3, a similar thing. So here we look at these w's. Now they depend on whether d is even or odd and similar norm condition. So here we will show that c of w over 3 is a generator of the ring class field of conductor 2f. Okay, so so the way we start this is first by proving some identities between these continued fractions at various arguments. So here's one for v of tau and v of 2 tau. And notice that it's similar to the one for r of tau and r of 5 tau, if you put it in that form. And then for case p is equal to 3, there are similar identities. The way we proved them is by using, there are several ways of proving them. We used the theory of modular functions and Ramanujan theta functions. And there are some combinatorial methods also that give many elementary proofs. So here also this identity between c of tau and c of 3 tau can be put it in this form. similar to the R of tau, the Rogers-Ramanujan continued fraction. And then we prove a few more transformation equations. V of -1 over tau in terms of V as a linear fractional like that, and then squaring gives us the second equation in that form. And also we have a quotient of eta functions like that we use in some of the proofs. Similarly, we have a similar result for case p equal to 3 also. And then we define two new modular functions in both cases. In the case p is equal to 2, we look at these two new modular functions, p of tau and b of tau, written in terms of both the Weber-Schlafly functions, f1 and f2, as well as the infinite product expansion. And in the case p is equal to 3, we also do the same thing. Here I'm calling them alpha and beta, written in terms of the Dedekind eta function. So these alpha and beta actually lie in the field of modular functions for those congruent subgroups also, and they do make the solution of the cubic Fermat equation in that form. Okay, so now that we have these two new modular functions in each case, the next thing we do is prove some identities between these new ones. For example, here are some between p of tau, p of 2 tau, and corresponding for b. And in the case p is equal to 3, there are some relations between alpha and beta at various arguments. And now we connect these new ones with their corresponding continued fractions. So in the case p equal to 2, the continued fraction v of tau is related to these two new modular functions p and b in this way. Again, the proofs are, so here I think we used Ramanujan's theta functions, the f of a comma b and q series, the kind of stuff you may see in Bruce Burns' notebooks on Ramanujan. I use that very extensively. And for case p is equal to 3, similarly, I'm relating the cubic continued fraction with alpha and beta in this way. Okay, now coming to our main results. So the first result in the p equal to 2 case is that for such a W of that form, which is the same form I shown in the abstract, we showed that we show that V of W over 8 generates this field, the field compositum of the ray class field of conductor P2 prime cubed, compositum with the ring class field of conductor F, and that they have the degree 4 times the class number. And we use discriminant arguments, counting degrees, and prime factorization in proving this. Again, I know I'm not showing you the proofs here. And another result here is if tau2 is the Artin symbol for this prime ideal P2 for this extension, and C is given by that, it's always either even or odd, and C only appears as the power of -1, so it only affects the sign here. We show that when you apply this automorphism tau2 to pi, which is given there, this is what you get. We use this in the next result to show how you get periodic points by applying these automorphism. And similarly, in the case p is equal to 3, we show this. So the first lemma we show is that beta of 2W over 3 generates the ring class field of conductor 2F for that corresponding W. And another byproduct that we use here is that the ideal is not ramified in the field adjoint to Q by C of W over 3. And we show that C of W over 3 generates omega 2F using similar arguments. First, we show that it lies in omega 6F, and then we use some arguments to bring it down to omega 2F. Okay, so finally, the periodic points results. So, so the last thing we show is that this generator, V of W over 8, so those values happen to be periodic points of this algebraic function f hat, and their squares are periodic points of the bottom algebraic function t hat. And in both cases, the period, or the minimal period, is the order of this automorphism tau 2. After that, we show that these are the only ones. So in addition to the fixed points, 0, sigma is a constant, -1 plus square root of 2, I think, and its conjugate. And all the conjugates of these values, v of w over 8, are the only periodic points of this function. And then a similar result for p is equal to 3 case. So here also we show that the generator c of w over 3, now we need a 2 next to it. So those make periodic points of the algebraic function, this Gothic f, defined by y is equal to the German f of z, whose minimal polynomial is this equation. In other words, if you take this equation and solve it for y, that's the algebraic function I'm talking about. It's going to be a cubic, so it's not going to look pretty, so I just wrote it like that. And then we show that these are the only ones, in addition to these fixed points that you can calculate. And then lastly, I show an example that I computed. So in the case p is equal to 2, for d is equal to 15, so here we want d to be -1 mod 8, so 15 is a possibility. So I first calculate the minimal polynomial of pi, which is b15, and then the minimal polynomial of v of w over 8, which is f15, which gives you an octet equation. But looking at the coefficients, you can reduce it to a quadratic, and then solving it tells you that this is one of the roots, and we used Maple to check approximations to confirm that this is the value for that corresponding w, 7 plus square root of -15 over 2. And similarly, in the case p is equal to 3, for d is equal to 8, we use this substitution where we get a sextic polynomial that factors into quadratic and quartic. The quadratic roots give you fixed points, and solving the quartic gives you a periodic point in this form. So in summary, this is what we basically did. So this was our approach. So we start with a continued fraction that can also be represented using an infinite product expansion. And then we first use the theory of resultants. We compute a lot of resultants and look at the discriminants and make a conjecture, and then determine what fields some of these values could generate. And then we take this Artin symbol. So once you have a generator, we apply it to successively to that generator, and until we get back to itself, because it has an order, it's an automorphism, so thus giving you periodic points. So here's the last two questions, almost done. So here's a question one could ask. So if you're given a continued fraction like one of these, what field is generated by a value of it? From some general results, for example, Schertz's textbook on complex multiplication tells us where those values lie, but which one does it generate exactly? And then another question, does this happen for every prime? Meaning, given a prime, is there a continued fraction whose values give you periodic points and generate certain ring class fields? So here's a conjecture that is missing a lot of details. I put q power 1 over p corresponding to the prime p here, and p over n is the Kronecker symbol. So for an appropriately chosen w, the values of this continued fraction in the form w over p will make periodic points of an algebraic function that is yet to be determined, and it's coming from the identity that is satisfied between f of tau and f of p tau. So, so currently we are looking at the case p is equal to 7, but it still has ways to go. And then we are also looking at to see if we can maybe classify the pre-periodic points also in these cases. So I will just stop here. Thank you.
Thank you. Since we're running